Last time we defined the notion of a Turing computable function. We're going to take a little bit of a leap of faith now, I'm afraid. Because we're gonna, in what follows, we're gonna assume the so-called Church-Turing thesis. The way it's formulated here, it's not really a theorem, but a thesis. The thesis says that a function is effectively calculable if and only if it is Turing computable. Since we don't define formally what effectively calculable means, this is really not a theorem, but a thesis. You can interpret it, for example, as saying that whenever we have an informal algorithm to compute a function or solve a problem, there is a Turing function or Turing machine that also computes it, and vice versa. The thesis, however, has many underlying theorems, namely that, for example, if I can compute a function using a Python program or a C program, then it's Turing computable, and vice versa again. So the thesis itself has a lot of formal support, in the sense that every notion of computability or rigorous notion of computability that has been developed over the years and decades has turned out to be equivalent to Turing computability. And we will mostly appeal to this thesis now in the form that, instead of presenting a formal Turing machine that computes a function, which can be quite difficult in the sense that it's technically a little bit arduous task to write down these Turing programs. So instead of presenting a formal Turing program, we'll often just describe an informal algorithm that computes a function. The main goal of this lecture is to develop a coding mechanism for Turing machines and Turing computations. The framework that we'll develop here applies to much more than just Turing machines. It will allow us to code any kind of objects over finite alphabets, such as formulas. So this will be very important later on when we develop Gödel numbers for formulas over arithmetic and so on. So to start, every Turing machine, as we have seen, is just given by its program, which in turn is just a finite list of quintuples. And once the Turing machine is fixed, these quintuples are over a finite alphabet. Namely, the Turing machine has a finite set of states, let's say Q0 to Qn. They contain these directions, or instructions contain symbols, namely one or the blank symbol that are written on the cells, or direction symbols, L and R. So let's assume we just number this set here by entry number 0 to n plus 4. Then we can code a tuple sigma, a quintuple, over this set here, simply by using a prime product here with exponents. So we have sigma is sigma 1 up to sigma 5. And the code for sigma would be 2 to the sigma 1 plus 1, 3 to the sigma 2 plus 1, and so on, right? So we take the first 5 prime numbers and take the exponent given by sigma I, right, of the ith entry here, sigma I plus 1. We add 1 so that if we our entry 0, we actually get a factor of that prime into the code, so that we can have unique decomposition later on. As you can see probably already, we can use this kind of coding mechanism for more than just quintuples, right? By using the uniqueness of the prime decomposition for any kind of sequence, finite sequence over natural numbers. So n star is just sequences over finite sequences over natural numbers. And by just mapping sigma to the corresponding product right, of the ith or mth prime to the sigma m plus to the mth entry in sigma plus 1. Right? We call this the code of sigma. This mapping gives us actually an injection from n star into n. It's not a bijection because not every number, natural number, of course, is of the form 2 to the something times 3 to the something times something. Right? So we only get an injection, but important here is that this mapping is computable. Right? So given sigma, we can certainly compute this. And also, if we have given a natural number, we can decide whether that number represents a code, right? Whether it's of this form. And if it is of this form, we can retrieve by using unique prime decomposition, right? We can retrieve the entries sigma 1 up to sigma m again. There's a alternative way we could define a coding, although this will work only for sigma of fixed length, but we will often make use of that coding too. We start with a pairing function, right? So this is just a standard bijection between n cross n and n. Right? And one way to do it would be using this function here. And then we can iterate it by just saying, okay, we'll just, for instance, for m equals 3, we would just take the code of the pair and then take the code of that and take the pair with x3. And then you can, of course, iterate it. And sorry, this m should, of course, be an m here. And then if we work with fixed length, we actually get our sequences sigma of fixed length. We actually get a bijection between n to the m and n. So both codings, important stressing this again, are computable. So we can write a Turing program to compute it, to compute these functions. And moreover, it's also important that they are computable, effectively invertible. So here, since it's a bijection, we can just take a number and retrieve from it the tuple. Here, as I explained, we can, given a number, we can first decide whether it possibly represents a code. And if it does, we can then use prime decomposition to get the entries. So now we can define the Gödel number or index of a Turing machine. So a Turing machine program, as you know, is just a list of instructions. Each instruction is a quintuple. So let's take the code for each of the instruction and then form the code of that, right? The Gödel number. So we take codes, those are natural numbers, and then we code those natural numbers into one big number, and that we call the Gödel number of the Turing machine. The notation here is that P sub E denotes the Turing machine with Gödel number E. And E in this case is also called the index of the Turing machine. And phi sub E then denotes the partial computable function computed by P sub E. In the following, we'll just assume that every index, so every number is actually an index of a Turing machine. We saw that, however, that our coding is not bijective, so it's not onto, but since we can effectively decide whether a number is a code or not, we can just renumber everything effectively and then hence assume that every natural number is the Gödel number of a Turing machine. One thing we can note about indices right away is the so-called Penning lemma. Every partial computable function phi sub x has infinitely many indices. And the reason is that you can simply find, you can attach vacuous lines or instructions to a Turing program that don't change the function that it computes, right? So, for example, if you have a Turing program, machine program P1 through Pk, right, and let Q sub n be the largest state occurring ever mentioned there, right? So now we can just add lines of the form Q sub n plus I b q sub n plus I br. So these states q sub n plus I can never be reached from the original program, right? And therefore will not influence what the machine actually computes. Just as we can code Turing programs, we can also code Turing computations. For that, we need to first look at what does an instantaneous condition of a Turing machine computation look like. So after, for example, the Turing machine completed a step, right? So what do we need to know? We need to know the current state that the machine is in, the current symbol that is scanned by the read-write head, let's call that S1. So now we need to also code the contents of the tape, right? And that's potentially a problem because a tape is something infinite, but for us the important thing is there's only at any time of the computation there are only finitely many ones, and so non-blank symbols written on the tape. So what we need to know is only the content of the tape up to the rightmost one. Let's call this S1 up to Sn, and the content of the tape up to the leftmost one, right? So let's call it Tm up to T1. So this can be ones and blanks, but after Sn on the right there will only be blanks, and to the left of Tm there will only be blanks. So let's say we say a configuration or instantaneous condition is as follows. We write it as Tm up to T1, then we put in the Qi state, then comes the current symbol scanned and the rest of the content of the tape up to the rightmost one. So now this is again a finite string over a finite alphabet, right? And hence we can apply our coding method to these objects as well. Now let's assume we have a halting computation over a Turing machine, right? So this would be a sequence of configurations. Let's call them C0 up to C sub t, where C sub 0 is the initial configuration. So that means we are in state Q1 and then have the input written on the tape, and the read-write head is just sitting on the leftmost one. Okay. So now then ck plus 1 we say is the configuration obtained from ck by applying the transition function delta to the state the machine is in configuration k, and to the symbol that is currently scanned in configuration k. And then C sub t is the final configuration, meaning, because it's a halting computation, that there its state is actually Q0. Each Ci is then just a finite sequence of symbols, and we can hence can be coded using the method that we developed before, and having a code number C sub I. And we note also that C, the code number for the I plus first configuration, is computable from the code number for the ith configuration. And we can now take all these codes of the configurations occurring during the computation and put those again together in one big code, which will be the code of the computation, halting computation. Now this will be important later on, but we'll state it here already. Given a natural number m, an index e, and an input x, we can effectively decide whether m is the code of a halting computation of the Turing machine with index e on input x. And the way we do it is, of course, we try to unpack m, right? Assuming that m is the code of a computation, we try to unpack it. If it's not of the right form, we'll see it right away. Well, this is not the correct code format? Well, if it is the right code, we can unpack the codes for the corresponding configurations, and then see, well, is each of these codes actually the code of a configuration? If not, then then this doesn't code a computation. Well, if it is, we can look at these configurations and see whether, for example, C1 is the result of applying the Turing machine with code E to the input X, right? And hence we can obtain C1, configuration C1 from C0 by applying this program to this input. We briefly need to address how to handle multiple inputs. I already hinted at that in the first lesson on Turing machines, but let's make this a little bit more precise. So given input n inputs x1 up to xn, we represent them simply in unary. So unary meaning x plus 1, x sub 1 plus 1 many ones, separated by blanks. So we have here unary representation of x1, unary representation of x2, up to unary representation of xn. And we, as usual, we start on the leftmost one here. And then Turing machines can deal with these just as they can deal with single inputs, right? Of course, the program, if you want to write programs for multiple input, the program then has to take into account that there is an input given that might have multiple components here. But in general, on the structure of the program, we don't have to change anything. So any Turing machine P sub E computes a partial function on the natural numbers, so n tuples of natural numbers. And we denote this resulting function by phi sub e to the index n here, right? And of course, if n is equal to 1, we get the original notion of unary or single input partial computable functions. But again, any Turing machine program can be interpreted as handling multidimensional inputs, because the output does not change, right? Because at the end, if it halts, if it ever reaches a halting state, it just outputs the number of ones on the tape, right? So that's why it can be seen as, or interpreted as, computing a multidimensional function. And now we can state the two main theorems of this lecture, and those will really be of fundamental importance for everything that will follow. The first thing is the Enumeration Theorem, which says that there exists a partial computable function, psi, such that this is a binary function, right? It has two inputs, e and x. So on input ex, it will just compute or simulate the eth computable one-dimensional function, right? So with index e on input x. And you just, of course, the way you do is you just retrieve the program of PE from E and then simulate PE on input X using this program here. And this enumeration theorem, namely that we can simulate all possible Turing machines on all possible inputs by a single two-dimensional binary partial computable function, has then, and we have to appeal to the Church-Turing thesis here now, the consequence that there is a universal Turing machine. Because if this is partial computable, and every partial computable function can be computed by a Turing machine, well, this partial computable function then has a Turing program, let's say with index I. So there exists an index of a Turing machine, right? such that the two-dimensional function computed by the Turing machine with index I applied to EX is the or computes the ETH unary function, right? So on input X. So in this this machine here, right, this index called I is then called a universal Turing machine. So you can think of it really as a Turing machine that is itself a machine, but it can also simulate all other machines.